this is plus infinity, because that is lambda of the infinite. So this shows that for this particular sequence of functions, they are not dominated by the lemma function. And let me also say before I prove it, when you are going in exercises to use this theorem here, it's a little bit more difficult than, for example, the monotone conversion theorem. Because typically you will be asked to say, okay, here is a sequence of functions proving integral convergence, or calculate this integral here. And then you're going to use the dominated convergence theorem, and then you're going to find the W. So the idea is you have to find the W. It's not given to you in the exercise. All that is given to you in the exercise typically would be a sequence of functions shown here. So it is up to you to find a suitable W as a reference. And this is why using that is not very difficult to prove, but for example, if you want to prove the statement I made before, you would have to find a W that makes this. Okay, so enough about that, so let us proceed to the proof. And in order to prove it, we need quite a few facts about the superunit, so let me write those down. I want to have those in this proof. So we are going to use this quite extensively. So take a sequence alpha j of real numbers, or extended real numbers for that matter. Then we have the following facts. One is that, I'm sure you have seen some of them before taking them all. If I take these in for that sequence, it always exists, and it's always less equal to U2. Always have this. Then, secondly, if alpha is some extended real number, then I can consider the statement that the limit as j tends to infinity alpha j is equal to alpha and limit exists. This statement is equivalent to the statement that he superheap are the same. And that the value is alpha. So in other words, in order to check that a certain sequence has a limit, it is enough to show that the superheap are the same. Then the sequence converges, and the limit is its common value of these two values. Have you seen this before? Some of you not. A third statement. We also shall need. Yeah. Statement number 3. Here let us take another number, beta, and then we can consider, say, being nth as n tends to infinity of, say, beta minus alpha j. And I guess maybe I want beta to be a real number. I don't want to have infinity minus infinity. So that's why I take that to be real. This is always equal to beta minus mu sup. J tends to infinity of alpha. So in other words, if I have an expression like this, a constant minus sequence, and I take the in from it, then I can split it up, but I have to change the event to mu sup. And it's very important, it's a minus here. If this had been a plus, it would have preserved. If it had been plus here, it would be int here and the int here, but with a minus iterations. And it's, if you just think about it as super and int, it's the same thing. Suppose you have a bag full of numbers and you want to take the supremum. Then if you take all numbers and multiply by minus 1, then it's the same thing as taking the int for that, and then afterwards multiply by minus 1. Anyway, you can just take, so these are statements about the super limit, and those are the use. And what am I proving here? Let's go back to the long time ago. Say that what's the proof this here. Okay, so let's see how it goes. And I guess also another thing I will be using, so I can write it down here, is for 2. It says that if I had a sequence of positive functions, then the x j tends to infinity integral uj mu, and then I have an integral dx j tends to infinity uj mu, and there is an inequality here. Remember how it goes? Which is bigger? Let's see. Less equal to or greater equal to. The way we do is one if you, for example, were to suppose that's quite all about it, but we do this example here. If you take the lead in of these two j's, in this case it is 0. We do this example to take the into those with 0, so hence this will be constant 0. These will all be 1, so this will be 1. So in that example we have over there, this would be 1 and this would be 0. So hence it has to be like this. Okay. But as we also say for 2, the most difficult thing about for 2 is to remember which way the inequality goes. Right, so let us prove it. So prove how the effect theorem on dominant conversion. So so we have that all uJ's are less than that W and all respective uJ's converted to U. It is not difficult to see that this implies that also U is less than W. Hence, we have that uj minus u absolute value is less than uj absolute value w. This is the final inequality, and both of these are less than w, so this is less than 2 times. Hence again, we have that 2 times w minus uj minus u is always a positive function. So what we have done here is we have, from that arbitrary sequence of functions, we have now constructed a sequence of positive functions. And this we will plug into for 2. And in for 2, they have to be positive. We only use for 2 positive functions. Okay, so we get, let me find it, go into this in my notes. I get it right. So let us just see what it is. I can leave in infinity, and then I just take the sequence of function 2w minus uj minus u, the value u, greater or equal to, I could use more blackboard. Okay, here we just start. Integral dv. Maybe I should. I want a little bit of space to make it today. So. So let's try again. So dv tends to infinity of the integral, and that was 2w minus uj minus u up to the value u greater or equal to integral dv j tends to infinity 2w minus uj minus u at the value of dv. This is what two gives us. And then I want to somehow see what is on the left-hand side, what is on the right-hand side, and see that everything is well. Now, look at the right-hand side here. I know that uj converges to u. That means that if this quantity here goes to 0, that means that the whole thing converges to 2 times w. It even converges. And if I have a sequence which converges to something, then v infinity is equal to 0. So in other words, what I have here is equal to the integral 2 of 2 times w. Because this goes to 0, so the whole thing just goes to 2 times. And this, by the way, is a okay, and then this would require more work. We say v inf j tends to infinity, and then I take integral of 2w parenthesis u minus integral uj minus u du parenthesis like this. So here I just I break up the integral, and now I use this formula over here. I use this formula, and that will now, this is a constant, so this will be my theta. So this constant becomes 2w u, and the minus will change the integral into. So in other words, I get that that was equal to, so I get that this quantity here is equal to this one. I should, by the way, have mentioned one more thing. Over here, because one consequence of this is that hence integral over u du is less than integral over w du, and this is finite. So once I have this, I get that this is finite, and this implies that u is integral. And I should have mentioned that also here in the theorem. So this is part of the statement that u is actually equal. Okay. So given this, we have now arrived at that this quantity here is bigger than or equal to this quantity here. And now this is a finite number. This is the same finite number. So that implies integral of absolute value uj minus u, so u is less equal to. So this is what we do. And now we then finally say that, okay, 0 is less than u in j tends to infinity of integral uj minus u du. And this is because all of these numbers are positive. If we have a sequence of positive numbers, then the int is a positive number. And this is always less equal to the sum j tends to infinity integral over uj minus u du by this observation we saw before. And we have just shown exclamation mark, this is less equal to 0. This is what we do. So in other words, all these numbers are equal and equal to 0. So this proves that we have this again implies that if we have the sum and the int are the same, then we can use this fact here. So this implies that the limit as j tends to infinity integral uj minus u absolute value u is equal to 0. And this was precisely what we were. Okay, so nice argument, really just using for true, and then the rest is bookkeeping. Okay, for true, bookkeeping, and these formulas here. This is what it is. Maybe I have one of you, so I can just maybe this is now easy, and then we just quickly say like this too, and then we're done. We can take a long. Well-deserved weekend. Everyone except the poor TAs who have to break exams. So what we get now is that integral uj du minus integral u du absolute value by the famous inequality that I have been advertising. This is less equal to this. And this we know from 1 tends to 0. Then this tends to 0, and that's exactly the same thing as saying that this tends to this. And that concludes I thought here. And so on Monday I will finish. I'm talking Monday about the rest of chapter 11. Maybe I skip a few things here and there, but Monday we finish chapter